My name is Robin Augustin. I'm an associate professor at the University of Uppsala. I'm also coordinating the B-CRATOS project, and we would like to welcome you all warmly to our webinar series of the B-CRATOS project. And today's topic is on communication, especially on fat intra-body communication that is being used as the in-body communication technique for B-CRATOS applications. So I will start with sharing the presentation here. So let me give me a second here. So this is the presentation. Okay. I hope you can see the presentation now.
Yes.
Wonderful. So fat intra-body communication, it's also called as Fat-IBC, is about communicating through the fat which is available beneath the skin for every person, every human being. But no, it's not only limited to human being, but also it could be applied to mammalian systems or mammalian organisms. So let me give you a perspective of what intra-body communication is, and then we will, go ahead with that intra-body communication specifically. So when it comes to in-body communication, you're talking about human body-centric communication, or else HBC. And HBC is the mode of communication where you use one of the tissues available in the human body as a channel for communication. And we will also see what are those existing communication modalities in the realm of intra-body communication. We will also see that there are quite many state-of-the-art technologies, but there are some serious shortcomings with those state-of-the-art technologies and their shortcomings. We will discuss it in detail. Then we will go a little bit deeper into what fat intra-body communication is and what principle it is based on. And then we will also do a reality check on where we are in terms of the development of technology. And we will also discuss some of those applications that we are targeting currently. And then we will discuss a little bit about the future of the technology. So let me start with the human body-centric communication. So as I mentioned, for any communication to be human body-centric, it's essential that you're focusing on or you're utilizing one of the tissues that is present within the body as a communication channel. So human body communication techniques is predominantly used in body area networks. And body area networks are those network of devices that are either implanted or worn on the surface of the body. And they need the communication in between them in order for them to serve a specific purpose. And in most cases, the specific purpose might be diagnosis or monitoring, or it could be also actuation or delivering some sort of specific drugs to the human body system. So when it comes to human body-centric communication, you talk about different scenarios, namely on-body, off-body, body-to-body, in-body. So when it's on-body situation, you are talking about two nodes or more than two nodes that are placed on the same person's body. When it comes to off-body, then you're communicating from the body to an external source or an external node that is detached from the body. Then you have the body-to-body communication where two nodes on two different persons are communicating with each other. Then there are also these in-body systems where you have part of those devices that are implanted and part may be mounted on the surface, or it could be also completely implanted, two nodes or more than two nodes that are completely implanted but still talking to each other. So we have a variety of applications in the perspective of wearables and also implantables. So when it comes to wearables, you can think about the Fitbits, the smartphones also you could use as wearables. You could also think about shoes with force sensors and strain sensors that can measure your gait. There could be also pulse sensors that is worn around the wrist. There could be heart monitors which is worn around the chest as a chest band. And there could be also man-machine interfaces like exoskeletons that communicates with the brain and then helps the person to do specific tasks. So these are all coming under the category of wearables. And then we also have implantable technology where you're talking about deep brain implants for deep brain stimulation, for instance. Then you have pressure monitoring for blood pressure assessment. And then we have pacemakers, which is a common, or let's say an extensively used implant. Then, of course, you have stimulators that could stimulate muscular actions. Right. So the importance of HPC comes out when the importance of HPC is basically anchored around the whole point of Internet of Medical Things, because Internet of Medical Things is where the data pertaining to a human biological condition has to be relayed to an external world, or has to be relayed out of the site of the source to a different part of the body, so that you can do certain applications. Maybe it could be drug delivery, or it could be actuation, or a simple hand movement, or it could be just getting the vitals out of the body so that the patient can be monitored for an existing condition. So the IOMT, the Internet of Medical Thing, that basically brings together physicians and the care providers, patients, and also the people who can do the analysis on the data in one bundle, because they are all connected within the IOMT landscape. So this also enables remote monitoring and also creates a faster response in addressing challenges or conditions that calls for immediate attention when it comes to human body or human circumstances. This also creates new business models which can grow from 534 billion US dollars with a growth rate of 20% per year. Some keywords for you to remember in the course of this presentation is human body, because everything is going to be based on human body, and the channel. So the communication, for the communication, it requires a channel. So channel is important. And then another keyword is lossy dielectric properties, meaning that when it comes to tissues within the body, they have electrical losses or conductivity losses. This is of prime importance, because these losses are going to impart hindrances in the communication channel. So you have to take account for that. So that's important. Then the frequency of operation is important. And then again, you have other modalities of communication, such as capacitive galvanic coupling. And then also the paramount requirement here is the confinement within the body, because you don't want the data to be, or the signal to be leaked out of the body, that someone else could tap into or listen to that data, because it's a secure, it's a private communication that should happen within the body. So there are quite many standards that is available for intra-body communication. So as you can see in the band given here, there is HPC, human body-centric communication, medical implant communication services, wireless medical telemetry system, industrial, scientific, medicine related applications, and then medical body area networks, and so forth. So there are like different frequencies of electromagnetic spectrum has been assigned and licensed for those applications. And when it comes to in-body communication, or let's say human body communication in general, you can think about signals such as electromagnetic signals, and you could also classify the second category into non-electromagnetic signals. So you have electromagnetic and non-electromagnetic signals. Under the electromagnetic signals, you have the low frequency and medium frequency electromagnetic signals, and then you have high frequency, very high frequency signals, and microwave signals that will lie within the microwave frequency range. So when it comes to Fat-IBC, we will see later, we are mostly discussing the microwave frequency range. And in the non-electromagnetic signal category, we deal primarily with ultrasound signals or ultrasound waves. Right, so let's look into the other modalities of intra-body communication. So we have set of intra-body communication that is already existing as mature technology, some of which is galvanic coupling, capacitive coupling, inductive coupling, ultrasound, and also radio frequency coupling. And radio frequency coupling, when it comes to state of the art, is only known in form of low energy Bluetooth or Zigbee and those kind of protocols. So let's see what capacity coupling is. Capacity coupling is when the communication channel or the communication aspect looks at the body as if the body is a dielectric, and then you're putting electrodes on the body on one end, and you have the ground as a reference, and then you have another set of electrodes on the other end. And between these electrodes, you have the body as a dielectric. So you have this induction of the charges, that is basically the transfer of charges, which would also constitute to communication. So the requirement here is that you have grounds which are floating, and then floating ground makes a path, a completion path through the Earth's surface, as you can see in this image, and creates the closed circuit, right? And then when you have a transmitter sending signal, that it will induce the signal on the other end on the receiver in a capacitive fashion. So when it comes to capacitive coupling, it exploits the lossy dielectric nature of the body, uh, where, as I said, the tissue induces a potential distribution from the transmitter to the receiver. The frequency of operation is tens of megahertz, so it's not like high frequency. It's just, let's say, a medium-low frequency range that it is operational at. Then the transceiver and the receiver, they both are attached to the body, and the grounds are dangling, and they are floating grounds. And the body acts as a conductor of electric potential, and the ground acts as a return path. When it comes to galvanic coupling, the body acts as a battery. So as if in the case of electrolytic battery, so the ionic exchange within the bodily fluid contributes to the communication. So you have two electrodes on one end. Let's say if you want to communicate from the left hand to the right hand, then you have two electrodes placed on the left hand and two electrodes placed on the right hand. And between those electrodes, you have this body medium, which is full of electrolytes because we have blood, and where you have free moving ions, and those ion displacement will produce, current, or let's say data flow, and then that could be utilized for communication as well. So as in the case of capacitive coupling, this is also a low frequency technique. So maximum 100 megahertz is something that you can obtain. And it uses the human body as a channel to propagate the electrical signal treated by a pair of a couple electrodes. The difference between these methods, this method and the capacitive coupling, is that the alternating current is coupled inside the body instead of between the body and the environment. So that means that the signal is not leaking outside into the environment, as we have seen in the field lines in the images before. The field lines are confined within the body, but the whole body is used for the transmission. Meaning that if you are using two extra pair of electrodes to touch that body, the signal could leak out of the body because the whole body has the presence of the signal. And it doesn't need a floating ground signal or the environment to have a return path for the circuit to be complete. So let's say the downside or the shortcoming of this technology is that you might have electrolytic variation depending on the saturation level of the body, how well saturated or dehydrated the body is. The electrolytic content could vary. If there is a metallic external contact, there could be leakage of information. And again, it's essentially a low frequency technique, so the bandwidth is compromised. Then we have this inductive coupling, and inductive coupling is usually used for pacemakers. And inductive coupling is also a low frequency technique where you have this magnetic induction between the transmitting coil and receiving coil. The biggest challenge with this technology is that those transmitting coil and receiving coil has to be in close proximity to each other for having efficient induction. And there could be also problems with mismatching in terms of the field lines if you are disorienting the coils one from the other, meaning that they have to be almost superimposing in the positioning in terms of the implant and the external reader or the transmitter coil. So the distance or the range is a problem, the orientation is a problem, and also that the frequency of operation is low, so the amount of data or the bandwidth is also constrained. Then moving on, we also have ultrasonic waves that could be also used as communication signals. So since body is a let's say semi-solid object, you could transmit. It's a medium, so you can transmit sound waves through it. But the problem really is that the body has materials or tissues of different density, and when the sound wave interacts materials of different density, then it will encounter an aspect called scattering, meaning that the signal will not pass through. It will pass through part of it, but part of it will also scatter and could have multiple reflection and would create noise. So that's one thing. Another thing is also the range, because it will be lossy because of this scattering. So large distance transmission through the body is a challenge. So the range is significantly reduced in ultrasound communication. Then there is yet another problem, which is related to cavitation, meaning that if there is some air bubbles trapped within the fluids of the body, then it can subject to cavitation, where the small bubbles can vibrate in the presence of ultrasonic waves and can rupture, and this could create implosions within the body. So that's not a good thing to have. So these are downsides and shortcomings of ultrasonic wave communication. Then again, we come to radio frequency technique, which is electromagnetic communication. In electromagnetic communication, it is known that the body is a very hostile, let's say, or lossy environment for electromagnetics. So when it comes to Bluetooth or other electromagnetic kind of communication, body tends to absorb the signal if you try to communicate longitudinally from inside of the body to outside. Because, for example, the muscle tissue absorbs the signal and couldn't transmit the signal for longer distances because of the lossiness of the muscle within the body. So it's not ideally used for in-body communication, but for on-body communication it works. But still, when it comes to front-to-back communication in a situation where you have a sensor node that is connected in the front side of the body, and then you have a reader on the back side, then Bluetooth communication is line of sight communication. So if you don't have a reflective surrounding around the body, there is no way that the signal that emanates from the front side of the body would reach the back side. So there is a big downside to it when it comes to, let's say, off the line. I mean, whenever those sensors and actuators are not in line with each other, in the line of sight with each other, the communication will be affected. And this is also the case when you have certain nodes, one on the leg or on the hand, and there is another node that is on the other hand or other leg, because they are always moving, in relation to each other, but they come maybe at some point in the line of sight, but I mean, most of the other times they are in out of line of sight configuration. So in those cases, you will have, intermittent data cut age, meaning that the data is being inhibited intermittently because of the whole process of obscuring the signals by the body itself. So to list some of the shortcomings of the state-of-the-art technologies, we would need like an external ground for when it comes to capacitive coupling. We would need stable electrolytic concentration when it comes to galvanic coupling. And galvanic coupling is susceptible to external contact. You can also think about attenuation and cavitation when it comes to ultrasound signaling. Radio frequency communication is always line of sight communication, so you have to have the nodes arranged in a linear fashion so that they can communicate with each other. Distance is always a challenge. These techniques are all low bandwidth techniques, and they are also offering higher path loads, so long distance communication is difficult. Again, the security is on a low side because you can tap into the communication, and since you can tap into the communication, privacy is also compromised. And essentially, because of the low bandwidth, the data rate is also low. So for an efficient human body-centric communication, we have set of requirements, and we would like to see if we could get to that with the new technology that we are proposing. So the requirements are the following. So we need an immunity towards environmental changes, and that would mean that the technology should be functional irrespective of the environment the person is. For example, if the person is indoors, it should work. If the person is outdoors, it should work. While the person is sleeping, it should work. And also when the person is taking a shower. Because most of this technology will stop working when the person is taking a shower, because you totally ground the person and you will not have any more signals, being sent to the receiver from the transmitter, because everything would be grounded. Then, of course, this technology should offer the new technology should offer low path loads, should be location independent, should be equally functional irrespective of the location on the body, should be able to cover anatomical lengths. User comfort is important because you should not mutilate the body of the human being in order for the technology to work. So you should be at a utmost comfort situation when using it. Should ensure high bandwidth, high security, safety, and high data rate and privacy. So that's where we bring in this technology called fat-to-body communication, and fat-to-body communication is based on waveguiding principle, which is innate to human body. So it has not been explored before. We were the ones who introduced for the first time the concept of fat-to-body communication, which is based on the three-layer structure of the human body tissue that includes skin, fat, and muscle. Because you can see in this image, you see the cross-section of a real human body where the outermost layer is skin, the layer interior to it is fat, and the innermost layer is muscle. So you have skin, fat, muscle. When you think about the dielectric constant and dielectric losses or dielectric conductivity of those tissues, you can see that, I mean, this red line and black line represents basically skin and muscle. They are pretty close to each other. So they have a high dielectric constant and high conductivity, whereas the fat has a very low dielectric constant and very low conductivity. What does that mean? It means that, the skin and muscle creates a very solid boundary in terms of its electrical characteristics, a bit closer to the metallic side, so that you can confine the electromagnetic signal between the skin and muscle. And then fat is almost a dielectric, so it could easily transmit the signal through. So meaning that if you're able to launch a micro signal in the fat layer, because of the skin and muscle, it will get confined within it and then propagates through the fat further on, wherever you have the fat between the skin and muscle. And it is also backed up the principle called Zenek wave propagation. And Zenek wave propagation is the physical principle by which you have the short waves, short electromagnetic wave that travels across Atlantic and makes a connection between Europe and the US, for instance. Right. So there you have this wave that is confined between the ionosphere and the surface of the Earth, and then it travels through multiple reflections on the surface of ionosphere and the Earth, and then it propagates from one point to the other, irrespective of the geometry or the shape of the Earth. So it can go around. So it doesn't necessarily travel in straight lines. It can go around bends. It can go around curves. It can go around mountains and sea and ocean. So similar to that, we also have a scenario where you have the skin and fat and muscle. So you have a less lossy medium and a lossy medium when it comes to fat and skin. The same happens between fat and muscle. You have a less lossy fat and more lossy muscle. So the Zenek waves do exist between such boundaries where you have less lossy fat and lossy skin and lossy fat and lossy muscle. So you have the wave naturally confined within skin and muscle in the fat due to the Zenek wave principle. And you are able to propagate the signal from one anatomical spot on the body to the other under the skin. So in order to achieve that, you need to get to the right Brewster angle so that you can impinge the signal, the microsignal, through the skin into the fat, and then you can excite the Zenek mode. So that is the trickiest part when signing a front end to excite such Zenek waves, so that you can make a propagation in the Zenek mode, which would be continuous within the fat layer. Yeah, so that also that you can think about it in a quasi-optic situation where you have the Brewster angle, and with that Brewster angle you can go through the skin's dielectric structure, and then you can get into the fat, and then it excites the fat as a Zenek mode, and then you can create electromagnetic propagation within the fat layer. All right, so we have done extensive studies on Fat-IBC application, Fat-IBC testing in different scenarios. It's physical scenarios, it's communication scenarios, and so forth. So we really needed to know, like, okay, how the Fat-IBC communication would work, fat-body communication would work in different contexts. Because when it comes to the fat within the human body under the skin, it might be different. It might be varied between person to person because the morphology of human beings are different, because it's a large spectrum. So you can even think about a very obese person with a lot fat under the skin, a lot of fat under the skin. Then you can also think about like a very low fat, lean person or athletic person who has almost like 7% of body fat, which is like maybe 1 millimeter, 2 millimeter thick fat. So it's very thin fat. So we would like to see like what is the critical thickness that you would need in order for having a reliable communication. That's one thing. And there could be also regions where you have like flaring of fat, you have more fat, right? For example, around the abdomen, you have more fat compared to the limbs, for instance, the hands and legs. So you would also like to understand such scenarios, how the communication would behave or the communication channel would behave. Then also you would like to understand how presence of blood vessel will affect the fat channel communication. And again, the dynamics of the body, like how the bending would affect this channel, and how the front to back communication would manifest when you have the Fat-IBC in reality. So the very first experiment that we did was this three-layer experiment. We have had skin, fat, muscle, and we sent signal from one end to the other to see like how much of data, how much of the signal is being transmitted. And we saw that, and we empirically proved it that the fat layer of the human body provides almost 1.5 dB per centimeter path loss for fat interbody communication uh, technique. So that is much, much lower than any other state-of-the-art technique, meaning that we could span almost 2 meters, which is for average human being a sufficient length of the human body, where you can send signal within available, power limits, the signal from one point to the other, which would also ensure high bandwidth data because you can send 2.45 gigahertz signal with maybe 50 megahertz bandwidth, sorry, 40 megahertz bandwidth, or even 80 megahertz bandwidth, depending on what protocol you're opting for. So you can either use Blue BLE some sort of systems where you have maybe 20 megahertz bandwidth, or you can go for WLAN systems where you're talking about 40 megahertz and more bandwidth, so that you could also accommodate high data rates. We also did some preliminary experiments with sending actual data packets through the fat channel through a phantom model. It was not like, let's say, an animal model or a human model, but a phantom model that are replicas of dielectric constants of the human dielectric tissue dielectric properties. Then we saw that, okay, we without loss could send, I mean, almost 100% of the data packet has been sent without losses across 10 centimeter, which is not large length, but still it is good enough length to characterize the loss per centimeter. And then, as I said before, we calculated the loss to be 1.5 dB per centimeter, which is still much lower than what is available in the market or in research. So we also saw that in our in let's say impedance characterization, meaning that, okay, we are creating an artificial impedance by placing a piece of muscle in the fat channel to see like how large should that inhibition be in order for it to cut away the channel completely. So we see that we still have a reliable communication until unless the channel is 60% blocked. So such scenarios are rare, but still, even if it's 60% blocked, we still can have enough signals that can transmit reliable data. So we also have tested different flaring or converging mechanism inside the fat, where you have like convex kind of structures or concave kind of structures, where we saw that there could be from 2 to 4 dB variation in the signal received. So it is also in the acceptable range and will still be utilized for reliable communication. So for that, we have also designed specialized probes that could be used in bench setup so that you can characterize the channel. We also did extensive simulation studies in order to understand the effects of blood vessels that are traversing the fat channel. And we have seen that except for one configuration, which is rarely happening in the human body scenario, for all other configuration of the blood vessel traversal, the communication was intact, and you don't have any significant loss in the channel. Yeah, so in one of the configurations, which is basically the longitudinal arrangement of the blood vessels, you have had reflections because the electric field will interact with almost a conducting plane because the blood vessels are conducting, and then you will encounter more reflection. But such orientation of blood vessels doesn't happen naturally within the body. Then of course we also tried with different kinds of implant antennas and see like how it's behaving within the fat channel. So we could intuitively presume it's much more easier to excite the signal within the fat when you have a monopole antenna which is inserted through the skin and reaches the fat. And then if you can excite directly in the fat, then the channel loss is much less because you have a direct communication within the fat. Whereas if you have to traverse through the skin, then the skin layer will add to the losses. We also have studied different orientational mismatches with respect to the transmitter and receiver and how it would behave in terms of the losses. And we have seen that you have almost 10 to 20 dB differences with complete mismatch, like orthogonal mismatch of the orientation. But that is very seldom happening that you have such a large dynamic variation between the transmitter and receiver. But even if there is a 20 dB difference, it's still uh, uh, is enough for you to have acceptable, reliable signal levels for establishing communication. We also have studied the effects on the band, and then there also we saw that okay, it could be like 15 dB in terms of variation, which is also not too large for accepting for having a reliable communication. So what was most important was to understand how the channel would behave when it comes to front to back communication, and we have also seen that even for 40 centimeter circumference, I mean, 40, that would be 80 centimeter in total, but the 40 centimeter distance from the front side of the body to the back side, you still have almost minus 60 dB available for the communication, which is still substantially large or robust communication. So we see that in comparison to Bluetooth, we have much better reception of the communication signal in the fat channel compared to the external signal that comes around the body. But the Bluetooth will behave better if you have reflecting surfaces around you. For example, if you're indoors, if your walls around, then again, you have multi-hop path that can communicate from front to back. But here we are talking about like outdoor environment or is an anechoic environment, or even in shower or underwater where you are really relying on purely in-body communication. So we also have studied leakage, and we have leakage meaning that we have the signal sent through the fat channel, and we are interested in how much of the signal is escaping the skin, like normally leaking out. And we see that it requires the power to be 28 dB or more for the signal to be leaked out, and that power is not usually available within the battery-driven devices. So it's much as the battery-driven devices delivers powers much lower than that. So there is absolutely no leakage happening between the transmitter and receiver. But if you have like a very strong transmitter, then again you can expect some leakage. Then of course, within the consortium B-CRATOS, we have Lynx and Rosella, who's here in this seminar today. She and her team has designed antennas, monopole antennas, and pixelator antennas that are customized for fat channel communication. And here you see some designs and simulations of those antennas, and they were also practically realized and fabricated and have been measured. And then we see, nice results where you have like good coupling around 2.4 gigahertz for our required frequencies for these antennas. So these antennas are nice because they are low profile antennas and can be worn on the surface of the body. So we have different projects that utilizes Fat-IBC, and on different levels, you have Fat-IBC projects that involves patches that communicates from one point to the other, but sitting on the surface of the body. We also have system where you have measurements from a sensor that is implanted in the body, and then that communicates with the gateway that is worn on the body, and then the gateway communicates with the cloud. And then we also have B-CRATOS project where we communicate directly from the brain to a prosthetic hand and try to create a full duplex system, a complete loop system where you, from brain to the machine, you communicate, and also back from the machine, which is a prosthetic hand, you communicate back towards the somatosensory cortex of the brain. So you have a closed loop system so that you can not only control, but also you can get the feedback of the hand. And then we are also focused on creating a body-centric operating system that uses Fat-IBC as a data bus that communicates between different electronic parts of a, let's say, human computer or a human sensing and actuator system, which can be also, named as a cyborg, because the humans who have electronic or mechatronic implants or mechatronic appendage can be called as a cyborg, and they have to be governed by an overseeing software system, an operating system, and we are also developing operating system with which Fat-IBC functions as the bus, the data communication channel to connect different parts of it. So we also have done pig trials where we have sent data through pig's body, where we picked sensor data from certain sensors like intracranial pressure sensor. Then we use that data in order to actuate a robotic hand as a representative actuator. And then we also tried different combination of sensors streaming data at the same time, which was successfully done here at the hospital here at Uppsala University. So we also have done many interfaces that could be used for wearable application together with companies such as ST Microelectronics, a product called Syntec, and they were wearable patches. We also, as I mentioned, are working extensively on brain-machine interfaces using Fat-IBC, and then there we communicate directly from the brain to the hand and control those motors from the motor cortex. And also the hand is interacting with the external environment and you're getting the proprioceptive tactile information, and that is streamed back to the brain so that you can stimulate the somatosensory cortex and make a full duplex system so that you can cognitively integrate the mechanical hand or the prosthetic into the thought process of the human. So that's, you will have more acceptability towards mechatronic or prosthetic extremities. So in B-CRATOS project, we use the non-human primate for the demonstration, meaning that the monkey gets an implant, and through Fat-IBC, it controls the mechanical hand and does some tasks, which proves that, okay, you can relay the data through the fat channel of a monkey and make a hand move. But then again, you have to also remember that the monkey is a small animal and the fat in the monkey is thinner. So if it is working in the monkey, it should intuitively work in the human beings because monkey is already a hostile environment given that the thickness of the fat is too small. So we also work on bionics, and the idea is to communicate from the brain to different bionics such as mechanical hands and also exoskeleton so that you can directly from the involvement of brain, you can connect and control those devices. Here, this is an example of a mechanical hand that we have developed, which has quite flexible degrees of movement, degrees of freedom, where the wrist can do extension and flexion, and can almost act as a human hands. Yeah, almost act as a human hand. Yeah, this is also a research that our colleague Bob Stuyvesant is doing, which is about micro robots, and also the idea is that this micro robot could be communicated using Fat-IBC. The Fat-IBC can be an enabler in terms of bringing data for a micro robot to do real-time application. And this is a fantastic research which focuses on removing embolisms, delivering drugs, and so forth. So Bob Jackson is present in this seminar, and he's championing that. We also have established custom-made chambers in order to prove the Fat-IBC concept, meaning that when it comes to front-to-back communication, we are focusing on sending signal from the body through the body to the next other part, the back side of the body. So what we have to do is to cut any surface propagation that goes around the body, right? So what we are doing is like we are making front ends that are masked towards Fat-IBC for the Fat-IBC application, and then we put the whole phantom, which is the test subject, into an anechoic box or a semi-shielded box, which is separated by a septum, meaning that any transmission that would happen around the body is cut due to the septum, and the only transmission that will be remaining is through the body, through the Fat-IBC. So this is a more detailed view of how the chamber looks like, and we have a publication around it. And here we can clearly see that in comparison to Bluetooth, Fat-IBC behaves better in communication, in coupling, because it is totally confined within the fat channel, and then you're receiving better signal through the fat channel. Whereas Bluetooth is not functioning well because the septum sort of decouples the signal from left to right, front to back. So here we also have experimentation done for volunteers who are on the athletic and obese side, and we can also see like um, the performance of Fat-IBC is equally good in both cases. We would also like to discuss about some recent works that we have done, which has been published in IEEE Transactions on Biomedical Engineering, where we have used a similar septum-based chamber that divides the phantom of 3-channel Fat-IBC into two, meaning that you have two probes on two ends, and those probes should communicate exclusively through the channel, not through the air. So that's why the septum is introduced. As you can see in this image, You have signal that is leaking out from the transmitter, and it's present all around the channel. And while you are introducing that substance, that is cut, and then the signal that is present in the that is received at the receiver is the one that is propagating through the channel. And this is the actual image of is a real image of the actual setup. Here you can see a simulation where you could see like how the propagation is confined within the channel, which improves that you have the propagation mode, or let's say Senec mode, in the three-layer channel, which is confined to the fat. Hence, it's called fat-driven body communication. So we did different scenarios of testing, which includes implant-to-implant communication, implant-to-surface, and surface-to-surface communication, and all were phantom studies. And we have seen that the channel would behave as if the normal free space communication technique, or the free space channel, where you can use almost all modulation schemes of communication protocols in these communications. So from BPSK to, let's say, 512 QAM, it works perfectly when it comes to in-body communication. It works until uh, almost 500, sorry, yeah, almost 256 QAM when it comes to in-body, out-body, in-body, off-body communication, because you have the skin. So skin creates some losses, so you might not be able to really exploit the higher modulation scheme. So that's why, but still, it can be very high data rates, more than 100 megabits per second, still using 500, 256 QAM. So when it comes to on-body, which is the worst case scenario because you have two layers of skin to go through when it comes to fat communication, but still in that case, you can still use 256 QAM as the modulation scheme for communication. And as you can see that it deteriorates, especially for the on-body communication, it deteriorates further when you are using extra length, or if you want to communicate over larger distance, like 20 centimeter or 30 centimeter or even more. Let's say for 30 centimeter, it works until 16 QAM, which is still good for 64 megabits per second and higher, which is still sufficient for BCI, body computer interface, brain computer interface. These are some examples of how the S parameters, or the coupling between the signal, the coupling between the transmitter and receiver behave for different arrangement. The first one is in body, the other one is in body, out body, the third one is out body, or off body, out body. So here you can see the data rates of the communication. So you can see we hit like 100, close to 140 megabits per second with different protocols. So we use WLAN protocol, ST220, ST20, and ST40. With ST40, you can go up to 120 and above. Then it hits saturation, but this hitting saturation, that process is not because of the channel itself, but this is just because of the limitation of the hardware. So if you have hardware that could have a higher limit of transmission, then again you can achieve a higher data rate as well. So the fat channel is not really limiting the data rate. It's the only available hardware that we have used. I mean, those hardwares that we have been using in this work is off-the-shelf hardware. So in the near future, we are going to incorporate dynamics, meaning that we would have physical representation of movement of the body and see the influence of that movement on the fat channel communication. And we would also develop advanced fat channel communication theory. Example is Senec wave propagation, or multi-dielectric models, multi-planar dielectric models. We are also working on a paper where we would like to consolidate all the results that we have gathered in the B-CRATOS project in the non-human primate model. So then the future definitely is going towards clinical trial. We have already done some on-body communication, but the idea is to go ahead further on with implant communication, being that the interfaces of Fat-IBC will be completely implanted inside the human. And our vision is to move towards establishing an alternate method of communication that would not require the spinal cord. And this is going to be hugely helpful for patients who have been suffering from spinal cord injury. So the information that has to go from the brain to different other parts of the body is being cut because of the injury. So those patients can benefit from fat interbody communication because that bridge can be provided by the fat interbody communication technique. Thank you very much. And this is only being realized due to our collaborations across Europe and especially the B-CRATOS project. And we are thankful to our partners for the strong collaboration and the European Commission for the funding assistance and the guidance in research. Thank you very much for your attention. And if you have any questions, we can discuss that. Otherwise, I wish you all a nice evening. Thank you. Good afternoon, all.
Okay, that's okay from my side. If you want to start, Robin.
Martina, you can edit it. Maybe you can start
Yeah.
the introduction, then I can come in with the presentation.
Okay.
Yeah.
Please go.
Then,
Yeah. Now it's okay.
okay, good afternoon.